This is going to be lesson 10-4. We're going to be examining the extreme value theorem, and we're still in limits and continuity. Now, if you remember in pre-calculus, we found the maximum and minimum value of functions. We called these extrema because it represented the extremes of the graph. Now, the extreme value theorem states that within a continuous interval, there will exist a maximum and minimum. It's guaranteed. And so later on throughout calculus, these maximums and minimums, they're going to have meaning, especially in various applications, and we're going to learn more tools in how to find these. And so basically we call this an existence theorem, and there are going to be other existence theorems that we're going to learn. And the good thing about these existence theorems is it says, based upon these scenarios, we know that this has to exist. So in this first instance, it says given that 2x cubed plus 1, that's my function, justify that my function is continuous on the interval -2, 2. Well, if you remember back when we just studied polynomials in pre-calculus, we said that the domain of every single polynomial is -infinity to +infinity, which means that on that interval, it's going to be continuous. So let's take a look at this on the graph. So I took that, here's my intervals between -2 and we have +2. And so here's the -2, here's the +2, and so it's been graphed in that interval. So if I wanted to know what the maximum of this graph is, remember it's the highest value, and so that maximum there is it looks like it stops at 17. So 17. What is the minimum of the graph? -15. Where do each occur? So this the maximum occurs when x equals 2, and the minimum occurs when x equals -2. So looking at this one, what is the maximum and minimum value of this function? So what is the max or min of the graph? Now, just looking at that blanket statement here, we know that this is asymptotic. And because this is asymptotic, we know that this is going to go up together for infinity. So there is no maximum. And then we also know that we have an asymptote right here at 0. And so we know that this is approaching 0. Is it ever going to get to 0? And the answer is no. And so there's no minimum just for the blanket graph. But now if I establish an interval, it says on the interval 0, 1, what is the max or minimum? Well, on this interval now, so I'm basically slicing the graph from right here to right here on this image. It is a continuous interval. It can't include 0, unfortunately. So there's still no maximum because it's going up to infinity. But now right here, that's where it has to stop. So I do have a minimum. Now, what differs from this graph and the previous graph are the asymptotes. And once again, this is what makes limits so important, is right now I can't conclude what, if over the entire graph, I can't conclude what the minimum is. But with a limit, I can conclude that it at least approaches a certain number. So on this interval here, it says examine interval 0, 2. So from here all the way to 2. It says, why is there no minimum on that interval? Well, unfortunately, I'm dividing by 0 here. So there's actually a hole or an open circle there. Now another conclusion could be the fact that I'm not including that value, but maybe I'm not including that value because of the fact that I have a removable discontinuity here. So because of that, I don't have a minimum, because I can conclude maybe what value it's approaching, but it's never actually getting to that value. It's getting closer and closer and closer and closer. And so I can't definitively say this is the smallest value because there's another value that I can get closer to it. And so because of that removable discontinuity there, or that point discontinuity, it's going to create that situation where there's no minimum value. Now let's conclude this lesson. The extreme value theorem states that if a real valued function f is continuous in the closed and bounded interval ab, then f must attain a maximum and a minimum at least once. So if you remember in those examples, in that closed bounded interval, there was a maximum and there was a minimum. On the examples in which there wasn't a closed bounded interval, we couldn't find either the maximum or the minimum. Now remember, for the bounds to be considered a maximum, they need to exist themselves. So we're assuming here, like in this picture, even though this is not the case, those bounds have to be included for me to even possibly say that the bounds are going to be a maximum or minimum. If the bounds are not included, then we can't use them to determine what max and mins are going to be. Now this does conclude our lesson. If you have any other questions, please leave them in the comments.